Hi everybody, welcome to another installment of SUPA Chemistry. Today's notes we're going to deal with the dreaded significant figures and then some dimensional analysis. So a little bit of math. Everyone freaks out about significant figures and I'm not sure why. Okay, so sig figs are really just, all they are is they tell us what place to round our answers to. And you do have to use significant figures in your calculations in my class. Okay, so we're going to run through those sig figs and those rules and talk about numbers and things today. All right, so let's go ahead and start with sig figs. And like I said, all it is, it's used to round calculations. That's what we use sig fig for. Now, we have to start with types of numbers. So we have two types of numbers. First of all, they're exact numbers. And an exact number is, these are defined values. Or values that are not measured. Okay, so our defined values or values that are not measured. So the not measured part's an example. Okay, so let's say I have 5 apples. It's not a measured number. This is an exact number. Okay, so if I count something, that's an exact number. So 5 apples. Or I own 2 cars. The 2 would be an exact number. Now our defined values are our values of measurement that we define themselves. Okay, so we define how big 1 inch is. That is, that's an exact number. 1 inch is an exact number, and it's actually equal to 2.54 centimeters. Okay. 1 gram is a defined value. Okay, we define what a gram is. Okay, so that would be another example of an exact number. So we determine what a gram is. So these are exact numbers. These don't play much role in significant figures. Our second type of number are inexact numbers. And our inexact numbers are all measured values. Now, why are measured values inexact numbers? Well, all measurements always have some degree of uncertainty. The question is why? Why do measurements always have some sort of uncertainty? Right? And I'm going to bring this over here, and I'm going to bring in a thermometer. And I don't think there's any way that you can read this. Okay, but if we were to read this thermometer, I'll I'll zoom in just for fun, because maybe we can see it. I don't know. I don't know if you can see that or not. But, okay, so if we were to read this thermometer, okay, each tick mark is 1 degree Celsius. And if we look at the thermometer, it is between 21 and 22. Okay, so it's not 21 degrees, because it's a little more than 21. It's not 22 degrees, right? So it's in between those. So we have to estimate how far it is between 21 and 22, right? So when we measure, you must always estimate one place beyond the scale. Okay, you always, no matter what the measurement is, you always have to measure one digit beyond the scale. So since we're estimating, we're not exactly sure of that last digit. So the last digit, whoops, hold on, I gotta bring us back out. The last digit of a measurement is an estimate. We guess. You must always, learn this now, you must always estimate one place past the scale. So if my scale is to the tens place, I estimate to the ones place. That's what my answer would be. If I have a ruler that goes to the tenths place, my answer would be estimated to the hundredths place. Now, there's something called the uncertainty of a measure. The uncertainty of a measurement is usually plus or minus 1 of the last digit. Okay, plus or minus 1 of the last digit. We're going to talk about that. All right. So let's say that we were measuring something. Maybe, I don't know, maybe we're using a burette. And the scale is to the tenths place. We would read that burette, we would estimate to the hundredths place. We would estimate to the hundredths. So let's say we did a measurement and we came up with 0.13 and our units. We've estimated this digit right here. We're not sure that that's exactly right. Okay, we're not exactly sure. That's why there's a little bit of uncertainty about this measurement. Now, uncertainty, okay, if this is the real value, when we measure, we should be able to get pretty close. So this could be 0.12, 0.13, or 0.14. There's a range of numbers that it could be. All right, now if you can't get in this range when you estimate, it's a problem, okay? Because 0.11 would be really close to 0.1. 0.15, now we're way up halfway. So our uncertainty is this plus or minus 1 of this last digit, okay? So the uncertainty of this measure would be plus or minus 0.01. 0.01 above this and 0.01 below it. That's what the uncertainty would be called. All right, so let's say we have a scale to the ones place. That means we would have to estimate to the tenths place. So let's say that we do a measurement and it's, I don't know, 1.6. We're not sure of that last digit because we've estimated it. Okay, now what would the uncertainty be? Well, it would be plus or minus 1 of the last digit. So my uncertainty of this measurement would be plus or minus 0.1. 0.15, 0.16, 0.17. Okay, we should be able to get in that range. Okay, so that would be our uncertainty of that measure. Now, here's a question for you. Is this number and this number the same exact thing? Are they the same number? 0.5 and 0.50. And the answer is no, they are not the same number. Am I sure of this digit? The answer is no. Okay, I am only sure that it's greater than 0 but less than 1. So I'm sure of this digit. I have no clue. You know, I've got to be close, but I don't know about the 0.5. So my uncertainty is plus or minus 0.1. Here, this is the one I'm not certain of. I'm not certain of the hundredths place. Okay? So I've estimated way out here to the hundredths place. These numbers, I mean, they look the same, but they're really not, because now I am sure to the tenths place. Up here, I was only sure to the ones place. This is a much better measurement. Okay? This one is a much better measurement. Let's talk about precision. And when we talk about precision, we're talking about the agreement between measured values the agreement between measured values. So for example, let's say that I had a whole bunch of people come up here and measure the width of this piece of paper. Okay. And let's say that one person measured it at, let's see, what is the real value? Let's say someone came up and measured it to be 21.23 centimeters. And then another person came up and measured it to be 21.24 centimeters. And then someone else came up and measured it to be 21.22 centimeters. Someone else came up and measured it to be 21.4 centimeters. And then someone came up and measured it to be 24.74 centimeters. Someone else came up and measured it to be 15.911 centimeters. Okay, and someone else came up and measured it and it was 26.31 centimeters. Okay. this width does not change. Okay, so my question is, how is our precision? Okay, these numbers really should be all the same because this distance doesn't change. Right, so if we look at these values, our precision is very good. They're pretty close. But if we include the whole data set, if we include all of it, now we have these numbers that are way off. Our precision has gone way down. Okay? Our data set has become much more unreliable, okay, when we add these other numbers in. Now, precision is measured by statistics. Our precision, how good our data is measured by statistics. Okay, and if you are a science major, you're gonna have to take statistics. Statistics in college. Okay, so you have to have a statistics course so that you can go ahead and analyze this. We're not going to have to deal with statistics and precision in this class. Okay, so we're going to be okay. But really, when I talk about precision, we're talking about using standard deviation. For those of you that have had statistics. Okay. And what that standard deviation tells us, it tells us if we have acceptable data. That's what it tells us. Again, in this course, we're not going to deal with it, but when you get into college, right, when you go away to college, if you're in science or math, you're going to have to take a stats course. Okay, so that's precision. Our second part of a measurement is being accurate. Accurate. ACC, accurate. ATE. And when we're being accurate, this is an agreement with a known value. An agreement with a known value. So this is taking one measurement and comparing it to the real value or the known value. So let's go back to our data set. So these were all our measured values. Well, if I call the manufacturer, okay, they can tell me what they make this paper to, right? So maybe the known value or the real value was 21.24 centimeters. Okay, so now I can compare all these different measurements to see how we compare to the known value. That's called accuracy. How accurate is our measurement? Right? Now, how do we measure accuracy? Accuracy is measured using percent error. And I will expect you to use percent error. Okay? I will expect you to use that percent error formula. And percent error equals the known value minus the measured value all over the known value times 100. So real value minus measured value all over the known value or the real value times 100. And this will give us a percent error. Now, what do we want our percent error to be? Okay, well, we would love it to be 0. We would love it to be 0, all right? But in our case, it's probably not going to be 0, all right? We need to be, if we can be under 15%, that would be good, okay, for our purposes, right? If you start getting big percent errors, you can't just ignore it. You can't just say, oh well, it's okay. It's not okay, all right? So if you get a big percent error, you have to go back and you have to look at what's going on. Did you measure wrong? Did you do the lab wrong? Maybe you did some calculations wrong, all right? So if you get a big percent error, you have to go out and figure out why. And if you can't figure out why, you might have to do the whole experiment again, all right? That is true in this class, all right? So we're looking for percent errors under 15%. Now, I don't know how many of you like to play darts. Well, let's say we have a dartboard. And I throw my darts, and I'm aiming for, or I want, a bullseye. And I go, shoo, and I go, shoo, and I go, shoo. Am I being precise and accurate? Well, if I'm being accurate, I want to be here. I want to be right smack dab in the bullseye because that's the value that I want. All right, so I'm not being accurate. Precision is comparing measurements together though. My precision is actually pretty good because all these measurements are agreeing with each other. So in this case, I'm being precise, but not accurate. What if I do something like this? Well, in this case, I'm not being precise because the darts are all over the place, and I'm not being very accurate either because I want a dart here in the middle. In our third case, okay, and this is how I throw darts, it goes 3 bullseyes straight in a row. In this scenario, I would be both precise because they have all three darts right in the same spot, but I would also be accurate because they are in the spot that I'm trying to hit, in that bullseye. Okay, so this one's precise but not accurate. This is neither accurate or precise, and this would be both. Okay, so hopefully that gives you an idea of accuracy and precision. All right, so how does this work with significant figures? We're going to start with counting sig figs. Okay. Number 1. If there is a decimal point present, we start on the left side of the number and work to the right until you find the first non-zero digit. So let's look at this number, 0.01063. The very first thing you ask yourself, is there a decimal point? Is it present? And in this case, yes there is. If that's the case, you start on this side of the number. You start on the left side and we work to the right. Okay? Zeros don't count, so this 0 doesn't count. That 0 doesn't count. So this is the first non-zero digit. So this digit counts, and everything after it. Okay, so this digit counts and everything after it. So this would have 1, 2, 3, 4 sig figs. Let's try this one. 27.0000. First thing you ask yourself, is there a decimal point? The answer is yes. As soon as it's yes, you start on the left side. Is this number some number other than 0? The answer is yes. So that means this number and everything after it counts. So this would have 1, 2, 3, 4, 5, 6 sig figs. All right. If the decimal point is absent, if there is no decimal point, we're going to start on the right side of the number and work backwards and work to the left. So let's say that we have 7101100. Very first thing you ask yourself, is there a decimal point? And in this case, the answer is no. So we're going to start on the right side of the number. Is this number some number other than 0? No, so it doesn't count. Is this number some number other than 0? No, it doesn't count. Is this number some number other than 0? And the answer is yes. So that means this number and everything in front of it counts. So this would have 4 sig figs. All right. Well, what about something like 23? No decimal point. So we start at the right. Does that one count? Yes. So that one and everything in front of it counts. So this would have 2 sig figs. All right. Let's deal with scientific notation real quick. In scientific notation, the number of sig figs is listed. So let's say that we have a number of 3.17 times 10 to the third. Okay? These numbers right here are our significant digits, so this would be 3 sig figs. Okay. If I want to put 41000 into scientific notation, okay, with sig figs, so this has, well, if we look at this, there's no decimal point, so this doesn't count, that doesn't count, that doesn't count, that doesn't count. This one counts and this one counts. So there only needs to be 2. So we would write 4.1 times 10 to the 1, 2, 3, 4, 5th. Okay, so this has 2 sig figs, this one does. Okay, now I want to show you one other thing, and it's a little trick. If you see a number like this, well, let's use this number, 410000, and there is a bar over one of the zeros. This bar tells you that that 0 is significant. Okay, it tells you that that 0 is significant. In other words, when we count sig figs, no decimal point present, so we start here. That doesn't count. That doesn't count. This one does, so that's a yes, and that means everything in front of it, okay, is significant. All right, so this would have 4 sig figs. And if I wanted to put that in scientific notation, we would write 4.100 times 10 to the 5th. All right. Well, why do we need to know all this? Well, in reality, okay, we're going to calculate with sig figs. Okay, you're going to do your calculations with sig figs. The first thing you're always going to do when you're doing a calculation is you always do all the math first, all the way through. All right, so if you have multiple steps, okay, you don't round in the middle, okay? You don't round or you don't do anything. You carry all those numbers out until you get to the very end. At the end is when we round, okay? So always do all the math first. Then round at the end. Okay, so that's very important. You always do the math first, and then we round. All right, now there are 2 sets of rules when we're calculating with significant figures. Number 1, if we are adding and subtracting, we're going to round to the least accurate place. When you're adding and subtracting, you round to the least accurate place. Okay, so let me show you. Let's say we have 3 numbers that we're adding: 1.01, 1.017, and 2.3.